Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Us from Compaq Circ. He's been at Compaq for about 7 or 8 years now?
8 years.
8 years. Originally working on user interface stuff, but then he switched gears and got involved in a very interesting project developing a web crawler, and that's going to be the subject of his talk today. So,
thank you, Richard.
Welcome, Mark.
So I again apologize for the delay here. So today I'm going to tell you about a web crawler that Alan Hayden and I have been building for quite a while now. Alan pulled out of the project about a year or 2 years ago. Okay. So, but first let me give you a little bit of context. So we built this web crawler in order to do web characterization research, something we call web archaeology, which is the study of the content of the web as a whole, with the goal of finding interesting facts about the structure of the web, the type of documents that are out there, and so on. And that's difficult because the web is pretty big. In fact, it's infinite in size. It changes all the time, and it's highly decentralized. There are on the order of 10 million web servers out there. Okay, so over the years we have built up a whole hierarchy of tools. At the very top we got specialized databases that, for instance, can hold the link structure of the web in main memory and then run graph algorithms on that. At a level below we have things like the full text index that is being used, for instance, by Alta Vista. Actually, the connectivity server goes also in there. At the level below we are working on a storage system able of holding billions of pages on local disks. They can have a cached copy of the web around. In the very bottom you have tools for getting to the pages in the first place. One of them is Mercator, the web crawler I'm talking about today. Okay, so the original goal of the project was, as I said, measuring the state and the evolution of the web. And in order to do this, you need a web crawler. This crawler should be fast. In the best case, the network resources you have should be at the bottleneck. It should be distributed in order to be fast, so you should be able to increase the performance of the crawler by adding more hardware, more resources. It should be scalable, first in the sense that by adding more resources you can crawl faster, but also that when the web doubles in size, you don't need to buy twice as much hardware. You can just crawl longer and things will still work. So this means in particular that it cannot hold any data structure all in memory. It should be extensible, meaning it should allow users to extend the crawler to their own needs. And the reason for this is, of course, that when we started the project, we had no idea what people would want to find out. It should be continuous, so you can actually measure the evolution of the web, measure how pages change over time. And then it's also would be nice if it would be portable, if it would run on pretty much any operating system you can conceive. Okay, so let me tell you a little bit about how well we did in all those points. In terms of performance, our most recent crawl fetched 891 million pages in 17 days. That's on the order of 50 million pages a day. You can run the system on NT machines with as little as 128 megabytes of memory, but you can also, add more hardware resources and then go accordingly faster. Clients can plug in new components at runtime, and the system runs on pretty much, the system is entirely written in Java and therefore runs on any platform that supports Java. Alta Vista is selling it for those platforms here.
So Mark, the 891 million document crawl, what kind of hardware did you use for that?
I will actually talk about this. Is where 4 DexStation 20 DS20Es, each one with a single alpha processor, clocked at 667 megahertz, and each machine having 4 gigabytes of RAM. RAM is really a key factor here. But I'm going to talk about all those things in great detail in the course of the talk. Okay, so let me give you an overview of the architecture of a single crawling node, not the distributed system, just the one node case. So this is a multi-threaded system. There are many worker threads on the order of 500 which fetch and process documents. And those workers access certain shared central data structures. So one of those data structures is the frontier, where you keep all the URLs that you still have to download. Actually, we keep more than just URLs. We also keep, in the case of continuous crawling, a download history of those URLs. When was the document last downloaded? What was the return code? What was the checksum of the page? And so on. Another data structure is the set of all discovered URLs. So you can avoid adding the same URL multiple times to the frontier. So this data structure needs to support fast membership tests. A third one is a set that contains a checksum of all the document contents. So you can see if you have seen this content under a different URL before. So you can see if trees in the web were duplicated or if there's some aliasing going on. And of course, we cache DNS lookup results and robot exclusion rules and things like that. So to show you a picture, this is a block diagram of the system. You have the URL frontier here. When a worker thread gets ready to do more work, it comes along, dequeues or removes a URL from this set, from this frontier, uses an HTTP protocol module. Do we have a pointing device here? Well, uses an HTTP protocol module, an FTP protocol module, or whatever the appropriate one is to download the document. Loads into an abstraction called a rewind input stream, or RIS, which for small document holds the document entirely in memory and for large documents spills it out on disk. And this thing offers you support for reading the document multiple times. And then it first checks, the working thread checks if the document has been seen already, and if so, it short circuits any further processing. It will not analyze the same document twice. Otherwise, it will execute a number of user-supplied processing modules. So for HTML pages, for instance, you might want to extract all the links on a page. Or for also HTML, you might want to compute histograms of all the HTML text on the page. For GIF images, you might compute things like color histograms. And so these things are all user-supplied. In particular, the link extractor, which extracts links from HTML pages, the stream of links coming out of this go into a URL filter, which allows you to exclude URLs based on syntactic properties of the URL, like the country they're in or whatever. And so the URLs which pass this thing go to a URL seen test, which checks has this URL been seen beforehand, and if it hasn't been seen, it finally ends up here in the frontier and the whole thing iterates. Okay. So how do you configure this crawler? We have a number of ways to do this. We ourselves just give it a configuration file, encode it in the form of an as expression. Alta Vista built, of course, a GUI around the whole thing. So you can say things like how many worker threads you want to have, what seeds you want to start off. You could supply either a list of URLs here or the name of a file that may contain many seeds. Alta Vista typically uses on the order of 200 million seeds. A filter that excludes or includes paths that allows only certain URLs. This particular filter would allow only URLs in the domain Germany that are not on a blacklist. Blacklist is the name of some file here which contains patterns of the URLs that you want to exclude. You can supply a protocol module. So here we say we use a special HTTP protocol written for Alta Vista, which does things slightly different than the normal HTTP protocol. And then you can supply some number of analyzers. You notice that protocols have on the left-hand side the scheme name like HTTP or FTP or HTTPS, and then on the right-hand side the name of a Java class. This is a full package class name. And the same for analyzers. On the left-hand side is a MIME type, and you could use stars there as wildcards. You could say text/star. On the right-hand side, again, the name of a Java class. And you can also specify here more configuration parameters. Okay, and so those things, they are loaded at runtime. The system is really, yes?
I was going to ask a question about seeds. You mentioned that Alta Vista uses like 200 million seeds.
Right.
Is that for performance, or could you get a complete crawl if you start with, say, 10 seeds, for example?
So the answer is no. You could not get a complete crawl. There was a paper actually at WWW9, which won the best paper award, that showed that the web is not a strongly connected component. Alta Vista has a URL submission mechanism. So they have a lot of URLs that are submitted to them that are not reachable from the strongly connected component. Right? So they need.
So those seeds basically are ones that people have submitted using the
That's correct.
mechanism.
So is the implication here that there are 200 million disconnected components, or
No.
this is just the union of all the things that have ever been submitted?
The implication is just that Alta Vista puts 200 million things in there. In the particular experiment that was described in this W.9 paper, the component which was not reachable from the strongly connected component, about 44 million URLs. This is that the thing looks like this. There's a strongly connected component here. Here is a set of pages that is reachable from the SSC, but you can't go back. And then here's a set of pages that you can't get to from the SSC, but they lead to the SSC. And then there are tendrils around this. So, actually, I would take this whole paper with a grain of salt because, right, there were issues with this paper. The raw data was computed using Alta Vista's first crawler, which had bugs in the link extraction code. So, I wouldn't feel too confident about this. Okay, so, but now let me move on to the first juicy data structure, the URL frontier. So the URL frontier contains a set of URLs to download. Its three primary methods are add a URL to the frontier, get a URL from the frontier without actually removing it, and then finally removing it from the frontier. The reason why peak and consumer split up into two different methods is for reasons of checkpointing. You want to, right, if the crawler checks during, if the crawler crashes during a download, you want to not have changed the state of your system. Okay, so this data structure should scale to billions of URLs, so it's clearly not feasible to keep all the URLs in memory. They need to be on disk. And it's responsible for preventing web server overloads. It should not be, you don't want this 500 crawling threads to hit on the same web server. The web server would probably crash very fast. And finally, this thing is also responsible for prioritizing URLs in the case of continuous crawling, that you download URLs that change more frequently or have historically changed more frequently, that you want to download them also more frequently. We built many alternative implementations, so I'm going to go into some of those. This is the simplest one we came up with. So we have our frontier object contains a bunch of FIFO queues, one FIFO queue per worker thread. Each worker dequeues only from its dedicated FIFO queue.
You have a fixed number of worker threads?
That's correct. We have typically 500.
How do you tune that number?
Well, if we are not in the situation where we're network limited and we have idle cycles, we increase the number of threads, and eventually we don't have idle cycles anymore.
So why didn't you make it dynamic? To have the system to look at the CPU utilization and create more threads?
That would be very hard to do in Java. I mean, you could assume that in a Unix system and then, do a top or look at KMM, but we didn't. 500 seems to be a good number. Also, you will see from the design, it's actually very hard to change this number later on the fly. It requires a rewriting of the entire frontier once the crawl has been started. So anyway, so we have each worker dequeues from its dedicated queue, and when new URLs are added, what this thing does is it looks at the host component of the URL and checksums the host component in some fashion. So for instance, it could compute a fingerprint of the host, and then modulos this by the number of threads in the system. So each host will be dequeued into the same FIFO queue. In this case, all URLs with host component A end up in the first FIFO queue. And there might be other hosts in there as well, like all the Bs fall in here as well. But you're guaranteed that no A will go into any other queue. Okay, so net result of this is that only worker 1 will ever contact host A. So you have like a very basic politeness guarantee, yes?
So a lot of websites have host aliases. For instance,
Correct.
you can go to research.microsoft.com or www.research.microsoft.com and get exactly the same code. How's that?
Correct. So what we at some point tried to do was to use DNS to compute the canonical name. There's a CNAME request actually in the DNS protocol. Actually found that it really doesn't make a difference. The sites which are clearly, the real right thing would be not to use host names, but to use IP addresses. Right? We haven't, let me put it this way, it seems to work. We haven't received any complaints that we're hitting with more than one thread on any web server.
Do you know how much duplication you're getting? Or
Yeah, so the most extreme case we found was websites hosted by Mindspring. There we found about 4,000 different symbolic host names mapping to the same server.
okay. What's the average duplication? Do you have a sense?
My guess is less than 2.
Let's say you are just multiply crawling this.
What is that?
You are multiply crawling the multiple.
That's correct. But if we would use IP addresses, we wouldn't be. Now, I should really make this clear. All of this stuff is pluggable, right? So it would be trivial for you. It would be a one-line change to make a new frontier that would instead use a resolved IP address of the host component of the URL. It's like really a one-line thing. But we found that this works good enough, and this way we don't pay the DNS resolution overhead on the NQ side, which it turns out you discover URLs much faster than you download them. So
when you get new work requests,
yes.
this up use immediately, so simply separately into history of one big queue that you split into pieces and then store in memory and wait.
I didn't hear that.
So you have the input to the frontier that's coming from the thing that's scanning page.
Yes.
Right? And then somehow that gets turned into this set of sub-queues. Does that happen
Synchronously. Synchronously, yes.
As soon as it's so they're stored separately like this.
That's right. So the workers that which extract links will repeatedly call the add method of the frontier and insert URLs in a synchronous fashion. And then, I mean, there is an in-memory buffer at the head and the tail of the queue, and right.
Remind me again what the advantage was of having a single worker thread access the same host. So it's just sort of
It's in order to prevent host overloads. This gives you a very basic politeness guarantee. Only one thread per web server out there, which is not good enough, and we'll get to this in a second. This is just a warm-up exercise here.
I just want to understand. This is, I mean, this. If you sprinkled them among all the threads, the number of hits on a web server would be the same, right? So this is merely.
That's actually not true, because there's oodles of locality in on web pages. So if you would sprinkle them around randomly, or if the host would access those queues randomly, then it's quite likely that you would have a front of web pages on the same host hitting the tail end of the queues simultaneously.
So there's some coalescing going on inside of each queue then?
Well, right now we just look at the host name and we have a function that maps from host name to queue.
Oh, it's host names, it's not URLs.
That's correct, it's host
I'm
names.
sorry. Okay, all right.
Right. Here, this is this point here. Yes?
So you have this multiple poles, so why do you still need a central frontier?
Because we want, to the outside, we want to present a very abstract interface with just 3 entry points. And you will see in a second that we have many more implementations of this which all present the same interface to the outside but look different inside. So let me actually maybe to make it clear. So what's the problem with this one? Can anyone see a problem with this one? Host-limited intranets doesn't work well there. If you have only like 20 hosts left, and two big hosts happen to map to the same queue, you lose, right? You have fewer working threads than you could have in the best case. So the next design we came up with solves this problem by dynamically assigning hosts to queues. So now we have a FIFO queue in the front end. URLs are added there, and we have one FIFO queue per worker thread in the back end. And URLs are dequeued from here. Each worker thread, as before, dequeues URLs from its dedicated FIFO queue. But now, each FIFO queue contains URLs of only one host, and there's an invariant that if any of those FIFO queues is empty, then the top queue is empty as well. So what happens when a worker thread actually removes a URL from the queue? Well, either the queue is non-empty, in which case everything is fine and life goes on, or the queue becomes empty, and then the invariant needs to be reestablished. So now this worker thread reaches through here and goes to the URL at the tail end of the top queue. And it looks in a table on the side that says which host names are mapped to which queues at the moment to see if any other queue already contains URLs with this host component. And if so, it pushes the URL into the other queue and iterates until it finds the first URL that has not been claimed yet. Pushes it into this queue and updates the table. So the property of this frontier design is that on host-limited internets, you will get the maximum download rate within the basic politeness guarantee of crawling each host with at most one thread. You get maximum parallelism.
So this
If there are,
is an issue if you've got relatively small chunks of them.
that's right. And it turns out most corporate intranets are actually like that. You have lots of small web servers and a couple of big ones. We, of course, discovered this when crawling digital.com. Right? Okay. A little bit more complicated. So we did this on the extra web and received complaints. People said, oh, you're hitting my web server too hard, and I really don't care that you have only one thread. You hit me 60 times in the last couple of minutes. That's no good. So we want to have some way to back up. So in this design, there's again one FIFO queue in the front end and a bunch of FIFO queues in the back end, but there are now more FIFO queue than worker threads. So configurable multiple, actually, of the number of worker threads. And attached to each FIFO queue is a timestamp. The timestamp tells you, and again, I should say, each FIFO queue contains URLs of only one host. So timestamp tells you, when may I contact this host again? Off to the side here is a priority queue, which is implemented as a heap, which is ordered by timestamps. And so a worker thread that wants to do more work comes along, gets ahead of this priority queue, looks if the timestamp lies already in the past. If it doesn't, it waits around until it does. Goes to the queue, dequeues the head URL, or peeks at the head URL, downloads the URL, times how long it takes to download the document, multiplies this by some configurable number, say 10, and updates the timestamp of this queue to wait like 10x, 10 times as long as it took to download this document before contacting this host again. And that seems to be working really well. We typically configure our system to have 3 times as many queues as worker threads and to wait about 10 times as long as it took to download the document, which means that we would consume at most 10% of the resources of any web server, and in fact probably much less. And we don't get any complaints of the kind of, you're overloading my site. We get complaints of, oh, you are trying to break into my site. But these are usually eccentric people. Okay. So I think I said everything that's here. And so this is the most complicated frontier design. This one is in the back end organized exactly as the design just described, but it also has support for prioritizing URLs. So we can attach priority values to URLs. We compute priority values based on any property of the URL. So you could base it on syntactic properties of the URL, or you could also base it on a download history of the document. Has the document changed in the last 2 downloads? If so, I probably want to increase its priority. And so we have here one FIFO queue per priority level. The prioritizer looks at the URL, it comes in, computes the priority, and puts the URL into the appropriate queue. And then this blob here dequeues, when it's being asked from down here to dequeue the next URL, dequeues URLs in a biased fashion that is biased towards high priority queues. Does this make sense? Okay, so this was all I have about frontiers. Let's move on to protocol modules. So protocol modules are responsible for 2 things. First, they implement network protocols, HTTP, HTTPS, FTP Gopher, you have it. And second, they're responsible for parsing URLs. The reason for that is the syntax of URLs is actually dependent on the scheme type. FTP URLs have a different syntax than HTTP URLs. FTP can contain a username and a password. And they're pluggable components. That means they can be loaded at runtime. And you can easily implement your own protocols by subclassing, for instance, by writing one from scratch, or by subclassing the protocol modules we already provide. As a matter of fact, Alta Vista implemented HTTPS just by subclassing our HTTP protocol module and overriding the one method that creates a socket. with something that creates secure sockets. Okay. The next abstraction we have is rewind input streams. So this is the high-level objective, is we want to have something that allows you to download the document once, but then process it multiple times, running multiple processing modules over it. So we want a facility to rewind to the beginning of the stream. So this abstraction has the normal Java input stream interface. It can be loaded from an arbitrary input stream. Small documents are cached in memory. Large documents are spilled out to disk. And it also provides other functionality like fingerprinting URLs, fingerprinting the contents of a rewind input stream, or lexing, providing lexing support. So it's easy to build an HTML parser on top of this. Okay, so the next set of functionality is processing modules, which we also call analyzers. Again, these are plugger components. And clients can implement their own or subclass analyzer classes we provide. The most important ones we provide is obviously an analyzer that just saves documents to disks. So the AV save doc analyzer saves documents in the Alta Vista page file format. A host doc counter counts how many documents there are on any given host, and then a checkpoint time writes out a big table. The HTML link extractor extracts links from HTML pages. The WML link extractor from WML pages. There's an HDML link extractor which extracts pages from HDML pages, which are for wireless, for phones essentially. We have something that computes color histograms and so on.
Question.
Yes?
Is there a problem at this point with pages that have what appear to be links or buttons to the user, but they're actually generated by JavaScript or other scripting languages?
Yeah, and we don't solve this problem. So what you would need to do this is you would need to embed a JavaScript interpreter into an analyzer. And the obvious problem with that is you need to, constrain its resource use. What if you have some malevolent guy who...
Sure.
Right. It could be done, but we don't do it. We don't address it at all.
Do you have any quantification of how bad that might be?
Actually, I don't. So I'm going to talk a little bit later about experiments we did. And one experiment I don't talk about is we performed a number of election crawls for the US presidential election, also for an election in Israel. And it turns out in Israel, the various election-related websites had almost exclusively Flash content, where we can't extract any links from, right? Mm-hmm. So I think it depends a little bit on the context. Okay, so but this is the interface of the analyzer class, and there's a constructor, and there are a couple of methods for checkpointing, but all the work happens within the process method, which takes a document bundle, which contains, among other things, a URL, plus download history, and a rewind input stream, which contains the actual document. So how much work do you have to do to write a new analyzer? Well, here's the code for an analyzer that logs all URLs, the URLs of all pages that contain the infamous blink tag. And what you should get out of this is it's short. It's 28 lines. So it really doesn't take, and this is, honest to goodness code, right? No corners cut. It doesn't take a lot of work to build a new analyzer from scratch. Okay, so now at this point we have worked our way up to this point. So the next component to talk about is the URL filter. So as I said before, the URL filter provides a way to exclude URLs from the crawl. And it's described by an S expression, the configuration file. So you can say things like the URL must be in Germany and the URL must not be in the blacklist. You notice that we have here keywords like domain or URL set and connectives like and not. So you provide a set of standard leaf filters to accept URLs based on protocol, host/domain, path name, query part. You have it. And operations to combine them. And you can also write your own filters. So if this isn't a standard keyword, then it is interpreted to be a Java class name, and the system will go out and try to dynamically load the class and check that it's a filter. Okay, so now we come to the most interesting data structure of the entire system, the URL set. So this data structure is responsible for filtering out URLs that have already been discovered and are therefore already in the frontier, maybe even removed from the frontier already. And so it has one method called add, which takes the URL, and if the URL is new, it will eventually add it to the frontier. So you can think of it as set membership test. And it must maintain the set of discovered URLs. And it should scale to 1 billion URLs, so it's not really feasible to keep all the URLs in memory. And one important thing to notice is there are about 10 links on the average HTML page. Actually, we discovered in more recent courses the number of links seems to be going up, so more recently it has been closer to 17. And so there are on average 10 calls to add per downloaded HTML page. So if we want to download 600 documents a second, then we would need to be able, this data structure would need to be able to support 6,000 add operations. So the average cost of one add operation should be well under a millisecond. So, well, what can you do about it? Well, first of all, one easy trick to keep the size down is to represent the URLs as checksums. We use Raven's fingerprinting algorithm to do this, so 64-bit fingerprints. If you want to do a URL, a memory-based implementation, then you can use an in-memory hash table of URL fingerprints, and if you do a spine and overflow bucket implementation, then you can use the first couple of bytes of the URL to index into the spine, so you need to store on the remainder of the URL. So we were able to get this down to 5.3125 bytes per URL. So 1 billion URLs would fit into 5.3 gigabytes of RAM. However, since it's all written in Java, and most Java runtimes have stop and copy garbage collectors, the cost of this is really doubled. So what we did actually, we implemented one implementation that uses, that maps this hash table into non-garbage collected memory, into C space, and uses JNI to access the hash table. But I mean, still, such a thing is useful, yes?
So you got 5 gigabytes, you got 5 gigabyte hash table, basically?
Yes.
And you're accessing it basically.
Well, I mean, that's one implementation. I'm going to talk about the disk-based one in a second.
So do you have any idea how much time you're spending in data cache misses?
No. No. All I can tell you is that we are completely saturating the network. The network is a limiting resource for us. Yeah. Okay, but now, more interestingly is, what do you do if you can't afford that much memory? Which, of course, memory gets cheaper, but... so, here's the best disk-based implementation we came up with. So first of all, one thing to notice is that there's a lot of locality in the stream of discovered URLs. There are a couple of really popular URLs. Everyone links to Yahoo, right? So experimentally we found that a cache size of 2 to the 18 entries, shouldn't say 2 to the 16, should say 2 to the 18, is a sweet spot. Such a cache captures about, 70% of all discovered URLs. And so when a URL that's presented to this data structure hits in the cache, we can immediately discard it. Otherwise, we add it to a table. In fact, we fingerprint the URL, add the fingerprint to the table, and write the URL in clear text out to a disk file, and then store in a second column of this table the index of the clear text URL in the disk file. Okay? So eventually, this table here fills up. Right? This has, by default, 2 to the 21 entries. The unlucky thread which fills this up then goes ahead and copies this thing into a back buffer of the same size and swaps the disk file against an empty disk file. And then goes ahead and performs a merge sort of this table against a huge disk file containing all the fingerprints of all discovered URLs. Okay? So in order to do this, it first sorts the table by fingerprint, then performs the merge sort, and marks each URL, each fingerprint, which hasn't been in the disk file beforehand, marks it with 1 bit, has not been there beforehand. We actually encode this bit in the second column here. Once this is done, it resorts the whole thing, this time by the index into the disk file that contains the URLs in clear text, and Then it performs a linear scan to both this table and the disk file, and every marked URL is being forwarded to the frontier. Every clear text URL is being forwarded to the frontier. Okay, does this make sense? This operation is known as a self-join. I mean, one possible improvement of this would be, you notice that the time it takes to merge things in here is linear to the size of the disk file. As the disk file gets bigger, the merge operation takes longer. Eventually, the merge operation will take longer than it takes you to fill up the front buffer. If you would use a sparse implementation here, then you would assume, then clearly the merge time is linear to the size of this buffer. So you would assume that you could avoid this, but we never got this to work. It takes us actually about 4 times as long to then do the merge then to fill up the front guy. Okay, now we switch over to distributed crawling. So the basic idea is that you carve up the host space into one partition per crawling node. And we do so by taking the host name, fingerprinting it, and moduloing it with the number of available crawlers. One important thing is don't use in your fingerprinting function the same irreducible polynomial, because otherwise most of the queues in the frontier implementation will be empty. Okay, so this was an architecture of the one node system, and all we do now is we put one extra box in here, which we call a host splitter. So this host splitter looks at the URLs that come out of the URL filter, takes the host name of the URL, fingerprints it, modulos it. If it is on the same host, then it passes on, if it belongs to the same crawler, it passes on straight to the URL scene test. And otherwise, it streams the URL over TCP connection to the peer node that is responsible for it. And of course, things are batched up, so you get big transfer units. Okay, so a couple of observations. There is no central bottleneck in the system, right? There is not a single node where all URLs flow through. That's a marked difference to the way Google is architected, say. The load gets evenly distributed over the crawling nodes. All the data structures are fully partitioned. Each URL set has only the fingerprints of the URLs of its chunk on the web. It doesn't have the fingerprints of all URLs in the web. Same for the frontier, same for the DNS lookup cache, same for the robot exclusion cache. There is very modest memory overhead, namely the size of the buffers where we batch up URLs into bigger transfer units. And the communication overhead is well below 2% of the overall network traffic in the system. Okay, so now I'm going to talk about performance. So all the things I'm going to describe were done on hardware consisting of 4 DS20E workstations, each one with a single 667 megahertz EV67 processor. That's an alpha in 0.25 micron technology, and with lots of RAM, 4 gigabyte each. And the system had 72 disk drives with a total of 2.6 terabytes capacity. It's important to note here that you don't need such chunky machines. You could have instead have like a larger number of smaller Linux machines. The only important factors are the total amount of memory and the total amount of disk. Of course, everything is fully partitioned. This is a picture of the thing, and it looks beautiful. Spent some 2 days to assemble it. This is the topology of our network. The blue and the green lines are 100 megabit a second connections. The red line is a gigabit Ethernet. You can see that the bottleneck is those two links that we have an aggregate bandwidth of 200 megabits. It turns out our ISPs rate limit us at about 150 megabits a second.
So we're using CERT's main internet connection for this?
Actually, we have a dedicated subnet, yeah.
So you didn't bother anything else.
Right. And so one thing the Western Research Lab, actually the Network Systems Lab, did was it started a thing called the Palo Alto Internet Exchange, and then it sold off this thing to AboveNet. And so one of the deals we got in this transaction was that we get free internet access and we get a cage right at the backbone, right at the Internet Exchange. So A, we don't step on anyone else's feet, and B, we are actually close to the backbone. And we don't have to pay, which is nice. bandwidth used to be really expensive. So in December we did a crawl which we configured to use the distributed in-memory URL set, so the cheating one really. And we limited the size of the crawl to not exceed 1 billion URLs in order to keep the size of to limit the size of the in-memory hash table. And so we configured the crawl to download all content types. The average document size was 17 kilobytes. If we would have restricted ourselves to HTML pages, we would have gotten accordingly more documents per second, right? Because HTML pages are smaller than documents at large. And so we downloaded 891 million documents over the course of 17 days. And the crawl was network limited throughout its entire life. And particularly the CPUs were over 50% idle, and we had very low disk activity. If you can trust monitor. Okay, so this is the performance over time. The horizontal axis is days into the crawl. The vertical axis is pages downloaded per day. So you can see that it was like always around 50 million pages. There was a little dip here. This was around Christmas actually. And then at the end it goes up, which, as you will see on the next slide, is a bit of a red herring.
So when you get duplicate documents, how is that counted here?
Duplicate content, you mean?
Duplicate content, yes.
It's counted as a download. If we download the document, we count it. As a matter of fact, if we, of course we have to, before we download the document, access the robot exclusion file, right? And if a document is excluded by the robot exclusion, by the robots.txt file on the web server, we still count it as a download. Right. We really count DQs from the front here, if you will. This here is the same graph, but now showing the network utilization. Horizontal axis days into the crawl, vertical axis is megabits per second. You can see that we oscillate between 100 and 120 megabits of useful payload. Right, so this is,
What are the daily spec scan mean?
checkpointing.
Okay.
And this is Christmas. And so one thing you can see that this graph doesn't go up towards the end. So towards the end we got increasingly smaller documents, right? Which is because the further you go into the crawl, the more you will run into crawler traps, into automatically generated pages, and those tend to be smaller. Okay. Yes.
Crawler trap?
There are websites out there, some unintentional, some intentional, that generate infinite content. So do a search for Scott Pagan Idiot. This is a guy at the University of Illinois. He has a great website out there, how to keep an idiot busy. And it does computer-generated prose telling you about how to keep an idiot busy. Make him follow this link, make him follow the next link, and so on. And there are a lot of things like that. There are some people who want to thwart robots that collect email addresses for junk emailers, and so on. Okay. Here's a histogram of a pie chart showing you the outcome of download attempts. So for 81% of all documents, we actually got a status code 200, okay. For 5.94%, we got a not found. I was actually very surprised that this number was so small. I would have thought that more links would be outdated, but it's actually not that bad. 3.04% moved temporarily. 3.92% excluded by robots.txt. And then here, these are network errors, and then there's some small number of other outcomes. So the high level is here actually 80% of the web is accessible, which is better than conventional wisdom claims.
So when you get an error like this, would you put the URL back in the frontier to try again later, or would it stay?
Not in the standard configuration. We have another. So this thing has been used by many people, among other things, by the Internet Archive. We contributed about a third of their collection. And so for the Internet Archive crawls, we do this on network errors. We do 3 tries. So we attach a counter to this piece of state information that can be associated with each URL. George? This is something supplied by the web server on the remote end. You can stick a file robots.txt into a standard location, namely into the root of the web space. and this contains the prefixes of all URLs you don't want someone to download.
Do you happen to know whether, I guess the 404 number is kind of an estimate of dangling links in the web, right? Do you know
Right.
how that number's changed over time? I thought it used to be a lot higher.
I don't know online, but I would know offline. I mean, I have those tables for lots of crawls. Yes?
But this wouldn't count, 1,000 references to the same not found page, right?
That's correct.
Yeah.
Absolutely.
So you don't really know exactly.
Absolutely. It doesn't count bad links, but it counts bad URLs.
Right.
Now, my guess is that those things are actually pretty isomorphic because a lot of bad links are typos. Right? People misspell GeoCities. Distribution of content types. Text.html 65%. Images are 15% for GIF and 14% for JPEG. Then comes text plain. PDF is about 1%. PostScript doesn't show up. I vaguely recall historic data for that one. So a year before this crawl was done, JPEG was more like 4%. GIF was a little bit more. HTML was a good deal more. So JPEG is clearly on the rise. And my belief why this is happening is that the initial Mosaic browser was able to show GIF images inline, but would open external imagery for JPEG. And so once Mosaic died, people started to, realize that JPEG is better.
What about dynamic filtering? So ASP, JSP?
I can't say anything about this. What I look at is the content type field that is part of the HTTP header of the returned document. Right, so I don't look at the suffix of a URL, I look at the content type that's transmitted for the web server. IIS will say for an ASP page it's text/HTML. Will not say anything about ASP. Document size distribution. So you can see that most documents are between 512 bytes and, say, 32K, and it seems to peak around 8K. Again, we have historical data for this, and from all we can tell, it's moving in this direction here. It's moving to the right. Documents are getting bigger, which has, of course, a lot to do with the fact that more and more multimedia content comes online.
What's the speed at which it's moving to the right?
I would have to look at 2 papers. Over the course of a year, maybe 1 notch. Distribution of contents over host. So this graph shows you the number of pages on a web server, and here the web server. So this means that there are 8 web servers which have more than 1 million, have 2 million or more documents. And there's a total of maybe, 20 web servers which have more than 1 million documents, and so on. So you can see that this follows roughly a Zipfian distribution, which is sort of what you would expect. If you draw the same graph, not for number of documents, but number of bytes, interesting enough, it's not a Zipfian. Right? That suggests that the big web servers have overproportionally large content. So this graph was a surprise for me. I would have thought that everything out there follows a Zipfian distribution. That's not true. Distribution of content over top-level domains. Well, it's not very surprising. Most pages are on that .com domain. Germany figures at 8%, .net at 7.8, and so on. What's more surprising is, and this is web servers per top-level domain.
So Germany's more than org.
Yes, in terms of web servers. But look if you look in terms of bytes of content, then it falls very quickly down. So you could, for instance, say that the government, the US government, is operating very few web servers. I don't actually see it at all in this table here. I don't see in this table either. That's a bad example. It's in here. But what's that? It doesn't show up here at all. But here, there's a lot of content out there. So the IIS websites of the world do have a lot of good stuff or bad stuff or whatever.
Do you have any just just out of curiosity, do you have any intuition why Germany is so high on number of web servers compared to?
I think there are a lot of companies out there who want to have a web presence or brought a web server with one page online and say, content will be available soon.
Okay.
When you see a lot of domain parking everywhere, right? But it seems to be more the case in parts of the world that are less well connected.
Right. And I guess Germany's also larger than any of the other EU countries. Right.
Okay, so this is the last slide I'm going to show you about that part. So we did this experiment We went a long crawl over 57 days using a slower version of Mercator and downloaded about 350 million pages. And then we fed the links of those pages into a database that can store the link information in memory and compute PageRank values for each page. PageRank is a page quality metric roughly based on how many other high-quality pages are referring to a page. Okay? And then we grouped the pages by the day at which they were downloaded and averaged out their PageRank. The thing is normalized at 1, so the average page over the entire crawl has PageRank 1. And you can see that you discover all the high-quality pages within the first couple of days. So the implication is that if you operate a website, I mean, it doesn't really matter if you crawl for 50 days or only for 30 days. Most likely all the pages you really care about you will discover during the first 5 or 10 days. Okay, so we wrote a bunch of papers about this. We also wrote...
Question about the page rank. So does that... If you look at like pages that are returned by search engines, pages that people want to see
Right.
as hits in search engines, are those necessarily high page rank pages? Or could it be that...
Yeah, I think so. I mean, if you look at the spectacular success of Google, I mean, I think initially it was certainly due to their much better ranking function. And the ranking function is PageRank. Those days, Google also wins on coverage. There's a much better coverage than anyone else out there. Yes?
So what fraction of those 350 million pages are actually highly, these high-ranked ones? Do you have any idea?
A very small fraction. I mean, most of the pages out there are junk, right? I mean, you can see, like, down here, like, everything is, like, PageRank of 1/2 or so. I mean, okay, so we wrote a bunch of papers about the crawler itself, a couple of papers about the things we discovered when using Java, about the performance limitations of Java, how they could be fixed, and then also this gave rise to a bunch of higher level papers about the structure of the web done using this tool. Okay, so this thing has actually been used quite heavily. So we transferred the crawler to Alta Vista. First into the first takers were the Alta Vista product group. The Alta Vista search engine has been sold to 1,200 customers so far. So they all are running Mercator on their intranets. And it's also now used by all Alta Vista sites, both by the country sites like Alta Vista Germany and by the main site, which used to be in San Mateo and is now in Palo Alto. The second set of customers was the Internet Archive, and Remy Slater did all the crawling work here. The Internet Archive has at this point about 100 terabytes of pages in their collection, and we contributed 35 of those terabytes. Also, we did a specialty crawl from August 2000 to Inauguration Day. We crawled about 200 election-related websites once a day, and then around the time the election actually happened 4 times a day. And we contributed the record of those crawls, the pages, to the Library of Congress, which then went back to the archive. The archive built a time machine, and this stuff is now online. You can see of what websites looked like on November 8th, right, when Florida was happening. So it was very nice that the election turned out to be that interesting. And then finally, I mean, of course, this was an enabler for a lot of other web archaeology research at Compact Research. And, well, this is not the only distributed crawler. The most well-known ones are the Google crawler, the Internet Archive crawler, the Web Fountain crawler, and then a news crawler coming out of Stanford by Jung-Ho Cho. Our system is extremely similar to the Web Fountain crawler, but predates it by a couple of days. Also, Web Fountain is written in C++. The Google crawler has a central bottleneck. So, star topology. There's one node that is responsible for link extraction and donning out URLs. That's a shortcoming. The Internet Archive crawler is a very weird batch scheme where you do exhaustive crawls of 64 hosts at a time, and then you switch hosts. So, it doesn't seem like a very scalable design. And again, Cho's crawler, actually not too much. I don't know too much about it. He just finished his dissertation, and dissertation isn't online. But it seems to be pretty similar to what we're doing. And that's the end of the talk. Yes?
So, based on your experience, it seems like the bandwidth of the internet connection is really the limiting factor
Right.
of being able to do this network. So you did a bunch of engineering for the rest of it, but it sounded like it really, in some sense, that that got you to a lower CPU utilization, but didn't really contribute to the overall success in some sense, right? I mean, if you had, so how about this other work? I mean, is the bottom line that to do this crawling you just need, hundreds
So
of
this is the second crawler that Alta Vista is using. Their first crawler was able to download on the order of, I found 10 documents a second, they claim 50 documents a second. By comparison, this thing is doing 600 documents a second. So I claim it does matter. And I mean, you need to be able, if you want to operate a search service, you should be able to refresh your index once a month. Now, Alta Vista doesn't do this for different reasons, right? I mean, namely that they have severe retention problems, right?
So they were getting 10 a second over the same bandwidth interconnect, basically.
Over their interconnect, which is a different one but comparable. Yes?
So you described crawls as if they have a start time and an end time. Or isn't it the case that actually many of the big sites are just crawling continuously?
That's definitely not the case for Alta Vista. And that's really the only website I can speak about authoritatively. They do scratch crawls.
Why is that?
Well, I mean, for one reason, the whole index building mechanism is very much geared to be a batch process. They don't have good support for
So there's not
removing
any index computation.
in the particular indexing engine they are using. It's not easy to remove documents from the index. It's easy to add them, but it's not easy to remove them. And so what they do is they build scratch indices. And if you have this mindset, then it's very natural to also feed in a scratch crawl, right? Because then the set of pages you feed into the index build will have each page exactly once, each URL exactly once. If you would do continuous crawling, then you need to worry about how subsequent download of a page replaces the first one. So you need some storage infrastructure in the middle. They don't have that. Yes?
So do you do any analysis? Has anyone done any analysis of the C database to find sort of central points of the strongly connected components to?
No, I haven't, and I think this will actually be very interesting. So we are very naive. We always started Yahoo, and it seems to work. And I suppose you could easily come up with a set of Yahoo-like URLs, like Open Directory, or when Snap was still alive and kicking Snap and stuff like that. But the big search engines, they are in a position where they also get a lot of URLs through submission, right? And that's in a way a much better seed set, because it also leads to the far corners of the web. Yes?
Is there any fundamental reason you couldn't take your architecture and distribute it over a wide area in order to get around the network?
No, I don't think there's any fundamental reason. You have to worry a little bit more about latency. So when you stream URLs over, there's actually an act going on in order to guarantee globally consistent checkpoints. But actually I had a design for a globally distributed crawler. But you have to see, I started this research when Alta Vista was part of Digital.
Well, I understand why you didn't do it. I was just curious.
There is no fundamental reason. And we do have a paper design. But we had little incentive to really implement in the end. Yes?
So you mentioned the checkpoint, which I assume you do in case the caller crashes, you can restart it.
Mm-hmm.
Was that actually a problem? Or did it crash?
So most of the time we stop the crawler voluntarily. And this is usually because someone calls you up and says, you are banging on my side, and I'm going to call my lawyer, and I'm going to call up Michael Capellas, and I will not put up a robots-to-text entry for you, and you better stop. In which case, it's much easier to stop the crawler, put this guy in the blacklist, and restart it than to do anything else. The other thing, actually, which we did encounter is power outages. Right? I mean, you all heard about the power crisis in California, and it turns out Palo Alto seems to have its own problems, right? I mean, even before all this energy crisis happened, we had, 4 power outages a year maybe. I mean, bizarre stuff, like in one case, some restaurant, they dumped their frying oil into the sewage system, and then it piled up around the transformer and eventually caught fire, right, and took out the transformer. So a bunch of those things.
But in practice, let's suppose you ignored the blacklist in effect for Palo Alto Tucson Power Company. Would it be worth having the checkpoint, or is it, given that you're running mostly from scratch crawls, would it be easier to just...
I think it's definitely worth to have the checkpoints. I mean, it's open for debate how big the checkpoint interval should be, because checkpointing is a pretty expensive operation.
Right.
But so we do every 24 hours, and we haven't felt the need to make it any more fine-grained, which I guess says that you don't really crash very often.
Right. So you could probably run it without the checkpoint and not really have another...
Yeah, I don't know. It would be a pity to, like, if something happens after 3 weeks, then you lose that much data.
Why should it run slower at Christmas?
I have no idea. I mean, my guess would be that everyone is going to Amazon and doing their last-minute shopping.
Nothing
I mean,
inside. It's something in the net.
That's right.
Okay.
That's right.
Was it running slower, or were you just downloading fewer pages?
We were downloading fewer bytes.
Could
Yes.
the sites were offline.
Could be what? Sites are offline. Yeah, could be that sites are overloaded. Could be that the backbone is overloaded. Could be that the guys at the Internet Exchange all went home and some part of their routing structure got slightly glitched, but not completely. Who knows? Right. Yes?
So if the network wasn't the bottleneck, what would the next bottleneck be?
I think if you could get the network, if you could buy enough network bandwidth, then the URL set would come back again. And before we got to this stage, the URL set was a bottleneck. Right. And the way to now have the in-memory implementation, that's a cheat, right? If I use the disk-based one, then I still degrade over time. So I would want to push the crawl to 2 billion or 4 billion pages. I would definitely lose.
Let me make sure I understand this. In your distributed implementation, you have a different URL set on each of the machines, right?
That's correct. And each one contains only one nth of the URLs.
Right, so if I'm willing to essentially buy a big enough herd of PCs,
yes,
then I can always cheat, and it's not cheating anymore, right?
Sure.
Okay.
But your bandwidth communicating URLs, you discover, goes up linearly.
Well, is it 2% of the 2% network traffic in order to disseminate this stuff, right? So it seems like it'd be easier to simply go ahead and distribute to a larger number and go with the more cheating.
So we found empirically that 80% of the URLs on the web page are relative links, right? So you can be sure that 80% of the stream of discovered URLs will always go right through memory.
So there is locality.
Right.
Okay.
So only those 20% you will have like n-1 over n going to remote hosts. So if you push the n up, then the worst case you pay 20%.
Okay.
I mean, so Google is pretty secretive about what they're doing, but from what I understand is actually they crawl of all their machines. They have in the order of 6,000 Linux boxes. They use them all to crawl. So clearly they must have worked this out. I think the nodes communicate.
All right, well, thank Mark. Your slides going to be available somewhere?
I can mail them to Richard Seth. Or I can leave them on the machine here.
Yeah.
Should I do that?
Interested in some of Yeah.
Okay.
Let's get some of the stats out.
Actually, all the numbers are contained in a paper which I mailed to Angela, so I could mail you both the slides in the paper. The paper has the prose around it, which is
Okay.
helps.
That'd be great.
Just get this going. Escape.
Let's get this shut down.
Do you want to save the
Yeah.
changes?
No. Like the only change you made is that date.
Something like that.
Is it working a little faster now?
That's okay. Just forget about it.
I'm going to copy this to